Hello, this is Mr. Win, and this video is over graphing rational functions. So, rational functions are always in the form of f of x equals n of x divided by d of x, where n of x and d of x are polynomials. N of x stands for numerator in terms of x, and d of x stands for denominator in terms of x. And also note that the d of x is not the zero polynomial, because we cannot divide by zero. Transformation still exists, so you have the a, b, h, k. A is the vertical stretch, vertical compress, vertical flip, meaning reflective of x. B is a horizontal stretch, horizontal compress, horizontal flip, meaning reflect over the y-axis. H is a left to right shift, it's opposite. And then K is the up and down shift, it's normal. Do note for B, you'd have to flip the fraction when you say the horizontal stretch or horizontal compress. And also think of A as the multiplier for the whole thing. You could take that out as a GCF. Anyways, if you see a constant value for K, you have two options. First is you could ignore K, do the normal fraction stuff, and then move everything up or down according to K. Or two is turn K into fraction, combine with the other fraction, so you only see one fraction at the end, and then do the normal fraction stuff. Now there's going to be a lot of stuff on here. You have to go over everything. But one tip I have is always make everything one fraction. In fact, the numerator and denominator as much as possible. Our domain will always be all real numbers except for the x values that make the denominator 0, which we've been practicing. The solutions, roots, zeros, or x-intercepts are found by solving f of x equals 0. That means y is going to be 0, and we have 0 equals a fraction. That means the numerator needs to be 0 for that to be true, because 0 divided anything besides 0 is 0. The y-intercept is found by evaluating f of 0. That means plug in 0 for x, see what we get for y. And we've done that before. Vertical asymptotes, they come from the restrictions in the denominator that didn't cancel out. And these are the vertical lines where you say x equals that number. We have holes. These come from restrictions in the denominator that did cancel out. These are called points of discontinuity, and to find the y value, you plug in that restricted x into the reduced rational fraction and simplify to see what the y is. We also have horizontal asymptotes. They come from comparing the degree of the numerator and denominator. If the degree of the numerator is smaller, then there's only one horizontal asymptote, and that's going to be at y equals 0. Now, if you have a k value, you have to move that up and down. If the degree of the numerator is equal to the denominator, then there's exactly one horizontal asymptote. And that equation would be y equals the leading coefficient of the numerator over the leading coefficient of the denominator. You have to reduce that. It could be a fraction. So a of n is the lead coefficient of the numerator, and a of d is the lead coefficient of the denominator. In third case is that the degree of the numerator is greater, then there's no horizontal asymptote. There can only be one horizontal max. Now we have a slant asymptote. That's a special case. That comes from the numerator having a degree exactly 1 higher than the denominator. And that's also called oblique. But that oblique asymptote equation will be equal to the equation of the line when doing long division. You're going to ignore the remainder though. So you're going to do n of x divided by d of x, long division only. You could do synthetic if the bottom is linear, but usually it's not going to be. Alright, now that's all the way. When you graph, you're going to find all the information from the slide before. So the x-intercept, the y-intercept, vertical asymptotes, holes, and then the horizontal or slant asymptote. And there's only one of those things. It can't be multiple. Then you put all that stuff on the graph. The asymptotes will appear to cut the graph into sections. That's going to help us sketch later. Then you're going to plot a point between each x-intercept and each vertical asymptote. So pick x's and plug them in to find the y's, and use the reduced rational to make your life easier. And then last, you're going to fill in the smooth curves. Remember, make sure you don't cross the asymptotes. So here's an example. To sketch the graph, g of x equals 3 over x minus 2 instead just domain. So first we find the y-intercept. They said it is 0, negative 3 halves because g of 0 equals negative 3 over 2. So let me show you what they mean. Every y-intercept has x value of 0. So I plug 0 in for this x. That means g of x will equal, on top would be 3, on bottom would be negative 2. You move that negative to the front, so that's really negative 3 halves. That's where they got that. So I'm going to plot this. So the y-intercept is negative 3 halves. So about right here. Alright, they have the x-intercept. They say there's none because 3 cannot equal 0. And the solutions, the roots sections come from the top equaling 0. I mean, you can also say this. X-intercepts are found when y is 0. If I plug in 0 for g of x, if I give you 0 equals 3 over this, you could multiply both sides by the denominator. And I'll do like this. By x minus 2, or LCD you want to call it. That would be 0 equals 3. That's false. You can't do that. So there's no x-intercepts. All right. Then they talk about the vertical asymptote. That comes from the denominator. So we're looking just down here. That's obvious. X cannot be 2. So that's actually line x equals 2. That's the 0 of the denominator. So the solutions of the denominator are actually the asymptotes, the vertical asymptotes, and the solutions of the numerator are actually the x-intercepts. All right, so I'm going to draw that dotted line at x positive 2. All right, then they went horizontal asymptote. Horizontal asymptote, we look at the degree. The degree at the top, the numerator, is 0. Remember, the degree is the exponent for a letter. So that's x is 0 power, on the bottom is 1. Because the top is smaller, you use y equals 0. Unless there's a k value, but there's not. So they just said because the degree of the top is smaller than the degree of the bottom. So I'm going to draw that dashed line. That's also why we don't have an x-intercept, because there's an asymptote here. All right, so I kind of cut my graph into 4 sections. Now they pick some points. So pick a point between every x-intercepts and vertical asymptote. So we're going to do something to the left of 2. That's why they chose from negative infinity all the way to 2. They chose negative 4. Now, why would they choose negative 4? That was because they thought it would be easy to make the bottom. So let's try that. 3 over negative 4 minus 2. That's the 3 over negative 6, which is negative 1/2. They thought that was something easy to reduce, so they chose that. Now, you do not have to use negative 4 like they did. I actually would have chose, let's see, I would have chose negative 1. Yeah. So the question is, why would I choose negative 1 instead of the negative 4? If you look at this, what happens if I put a negative 1 right here? What is 3 over negative 1 minus 2? Well, that's 3 over negative 3, which is negative 1. I chose something that was easy to reduce, just like them. They chose to reduce fraction. I just chose a fraction that reduced the whole number. So those are points. They said the point exists negative 4, comma negative 1/2. So left 4, down 1/2. Here's a point right here. I just found another one. I actually said when you use the point negative 1, you also get negative 1 for the y value. So here's my point. Now, with that, we already have enough information to graph this bottom section. So I'm going to draw this curve. You get really close, it's like a C. Get really close to the line, but you don't cross it. And this goes down. I could actually pick something like, say, positive 1 if I want. Again, I could do, didn't have to use negative 1. Let's try positive 1. 3 over positive 1 minus 2. Well, that's 3 over negative 1. That's negative 3. So I know when we have positive 1, the y value is negative 3. If I plot that, positive 1, negative 3, here it is right here. But I can just draw this. All right, then they tried something on the right side. They from 2 to infinity, they chose positive 3. So the question is, why did they choose positive 3? And actually, it's going to be just like I did before. I'll leave that down there for y'all. Positive 3 makes this bottom super easy. 3 over 3 minus 2. Well, that's 3 over 1. That's just 3. So when x is 3, y is 3. So I put that dot on there, 3 comma 3. And that's enough. I can just say, oh, it gets really close to this, gets really close to this. We're just drawing the smooth curves. You can find more points, but you just need at least one to figure out whether the curve's on top or bottom. It tells you which section of the parts are, because we are not in this upper area. This is wrong, and we're on this bottom right section. That's wrong. So if you plug in a point, x value, and find the y value, it'll tell you whether you're on the top half or bottom half of each section. All right, and then did it say anything else? So state the domain. The domain here is all real numbers, except x cannot be 2. That was our restriction. That's our vertical asymptote. All right, let's try another one. Here, sketch that graph, 2x minus 1 over x. So they try to find the y-intercept. There's none, because when we plug in 0 for x, that's 0 minus 1 over 0. You can't divide by 0, so no y-intercept. To find the x-intercept, they solve the top. The numerator, if you do 2x minus 1 equals 0, you add 1, divide by 2, you get 1/2. That's why 1/2 comma 0 is a point. Let's put that on here, 1/2 comma 0. All right. Vertical asymptotes, you look at the denominator. It's by itself, that's just saying x can't be 0. So x equals 0 is itself the vertical asymptote. And that's also why we don't have a y-intercept. Alright, horizontal asymptote. We look at the degree. The top is 1, the bottom is 1. So we're going to divide. So we're basically looking at 2x divided by x. But really, this is 2 divided by 1. 2 divided by 1 is 2. So that's why y equals that line. Y equals 2 is our horizontal asymptote. So I'm going to draw that. Alright, we have our sections. We pick some points. We have to pick something between negative infinity and 0 on the left side of the asymptote. They chose negative 1. They pick anything they want, but I'll just save some time. When they picked negative 1, they got positive 3. So negative 1, positive 3. With that, I know I'm going to get really close to this and really close to this. Right, they picked something between 0 and 1/2. It's not much choices. They chose 1/4. So when I pick 1/4, they got negative 2. So 1/4, negative 2 is down here. And then they picked something from positive 1/2 to positive infinity. So they tried this. They got a 1.75. So 4, 1.75 is right here. So I now can draw this curve. Alright, that's it there. Here's another one. Sketch this graph. So notice they factored first. The top turned into this, while the bottom turned into this. Then they crossed out and they got this final answer right here, found with the restriction. Now notice, I always say you find the restriction before you cross out. There are actually 2 restrictions here. Can't be positive 3, can't be negative 1. So I'm going to tell you now, the domain, they didn't say it. It's all real numbers except positive 3 and negative 1. You'll see why in a second. Alright, so if we solve the top, x equals positive 3 and negative 3 are our 2 solutions. But 3 can't be in there, so that 3 is gone. So really only have x equals negative 3. If you want to, you can actually just solve the final part to see what the answers are, because there's no restrictions left in the final fraction after you reduce. Alright, so they have the x-intercept we just had. The y-intercept, they plug in 0. So if I plug in 0 for x, 0 plus 3 over 0 plus 1, 3 over 1 is 3. That's easy. 0, 3. Vertical asymptotes. Remember x is going to be 3 or negative 1? Well, the 3 canceled out, so that's not really a vertical asymptote, that's just a whole. But negative 1 is a vertical asymptote, so they have that. They said 0 to the simplified denominator. Horizontal asymptote, they divided the coefficients. You could use the final one. At the very end, we have 1 here over 1 here, so that's 1 over 1 is 1. Or you could do over this. 1x squared over 1x squared is still 1. I should have the y equals 1. They did some points, and they got all that. So one thing I do want to mention is this. They didn't state the location of the whole. They just said whole at x equals 3 right here. If I want to know the y value, to find the y value of whole, you must plug it in to the final equation. So I plug in 3 here and 3 here. That's actually going to be, let's see, 6 over 4, which is 3 halves. So that should be 3 comma 3 halves. That's where the whole is at. Whole at that. So here the domain is all real numbers except for this, negative 1, and this, 3. They couldn't use those 2 x values. Alright. Slant asymptotes, I want to say they're oblique, they're slanted. You must do long division, but here's what it looks like right here. Alright, so I'll let you read that. But here's the real problem. Sketch this. Now they're kind of bad when they factor the top. So I factor the top. I start with 2 roots, positive 2, negative 1. Restriction, vertical asymptote at positive 1. When they divided, they did long division. They didn't show the steps here, but make sure you now do long division. X goes into x squared times x. So I get this. Remember these 2 cancel out because they're the same. These 2 cancel out the same, bring out a negative 2. Negative 2 can't go to x minus 1, so that's the remainder. No remainder, that's the diagonal line right here, and I'll stop.